In the last few lectures, we had examined forced convection at high Peclet number. In particular, in the last two lectures, we had examined convection due to Taylor dispersion in the limit of high Peclet number in a pipe flow. This was considered in the limit where the Peclet number is large based upon the diameter of the pipe and the diffusion coefficient. And I physically told you why this rapid dispersion occurs. That is because if you have a plug flow, there is only molecular diffusion which is spreading the concentration field. Laminar flow, because of the velocity disturbance, velocity difference between the center and the wall, there is a range of velocities, and therefore, any initial plug will stretch out and result in a larger concentration variation with length, and that stretching out also promotes cross stream diffusion, and that is the reason for the diffusion for the faster diffusion in this case. We had separated out the velocity into an average part plus a fluctuating part, concentration also into an average part plus fluctuating part, and we found out that in the expression for the flux, the average flux across the cross section, it is cross sectional average of the flux locally, consists of two parts, the convective part plus the diffusive part. And in the convective part, the particular term that results in a non-zero contribution is the correlation in the fluctuations of the velocity and the concentration field, the correlation in the fluctuations about the cross sectional average of the velocity and the concentration. Now, the concentration field we had expressed in terms of the average velocity, average concentration and the fluctuation. Similarly, for the velocity, we had done a cross sectional average of this entire concentration field, and you got both the average concentration as well as the correlation in the concentrations. We had neglected the concentration fluctuation relative to the average concentration, because we said in the beginning in our assumption that the variation across the cross section is much smaller than the average value. Similarly, we had neglected the axial variation in the fluctuating concentration in comparison to the radial variation. Note that there is no radial variation in the average concentration, because you have already averaged it over. So, we had neglected the axial variation in the concentration fluctuation relative to the radial variation of the concentration fluctuation. And based upon that, we had got an equation for the concentration fluctuation in the radial direction. Solved that subject to boundary conditions and the condition that the average of that fluctuation has to be 0, and substituted that into the expression for the average flux. And we found out that we got a dispersion coefficient, which goes as the diffusion coefficient into 1 plus Peclet number square by 192. And that second term there is the largest term, the dominant term in the limit of high Peclet number. And with that, we had completed our discussion of forced convection. Now, I will start another topic, and that is natural convection. Let us say that I had an object of characteristic length Lc with surface temperature T is equal to T naught, in an ambient fluid with temperature T is equal to T infinity and density rho is equal to rho infinity, in the ambient fluid. If T naught is larger than T infinity, then the fluid that is in contact with the object will be at a higher temperature. The fluid that is in contact with the object will be at a higher temperature, and fluid at a higher temperature has a lower density in a gravitational field. Fluid at a higher temperature has a lower density in a gravitational field. And therefore, this fluid that is at a higher temperature will tend to move upwards. As this fluid moves upwards and it vacates the region around the particle, this object, the cold fluid has to move in to occupy that space. Okay. Cold fluid has to move in order to occupy that space. And because of this mechanism, heat is taken away from the object as cold fluid moves in, gets heated and then rises, taking away the heat with it in a plume that is there above this object. Okay. So, this is the process called natural convection. Okay. This is the process of natural convection. Okay. Now, the equation for natural convection, let us say that the object was at temperature T naught, the fluid at infinity was temperature T infinity. Okay. At steady state, if T naught and T infinity do not change with time, then the system is at steady state. The energy conservation equation is the divergence of rho times the velocity times T is equal to the divergence of the thermal conductivity times the gradient of the temperature. Okay. And the Navier-Stokes equations are divergence of rho times the velocity is equal to 0 and rho v dot grad v is equal to minus grad p plus mu, I should take the divergence of the viscous stress, okay, transpose, okay, plus rho times the gravitational acceleration, okay, plus rho times the gravitational acceleration. Okay, so, that is the body force, rho times the gravitational acceleration is the body force. Okay. We can make a simplification to the momentum conservation equation. Okay. If there were no flow, okay, if there were no flow, then there would be a stratification in the density, okay, in the momentum conservation equation. Okay. Okay. If there were no flow, you will get minus grad of Ps plus rho infinity g. Okay. If there were no concentration variation, if there were no concentration, I am sorry, if there were no temperature variation, then the body force would just be rho infinity times the gravitational acceleration. I can subtract out this, okay, the case where there is no temperature difference from the total momentum conservation equation. Okay, I can subtract out the case where there is no temperature difference. Even if there were no temperature difference, there would be a hydrostatic head. Okay, there would be a hydrostatic variation in pressure. That hydrostatic variation in pressure, when the density is a constant, is what I called Ps. Okay, and I subtract that out from the momentum conservation equation to get, okay, rho v dot grad v is equal to minus the gradient of the dynamical pressure plus divergence of mu grad v plus grad v transpose plus rho minus rho infinity. Okay. Infinity into the gravitational acceleration. So, this is the driving force. Okay. This is the driving force for the flow, the difference between the density at the object and the density far from the object. Okay. So, this is the driving force for the flow. Okay. Now, how do we solve these equations? As you can see, they are rather complicated equations. Therefore, we make some approximations. So, I should note here that this dynamical pressure, okay, P d is equal to P minus the hydrostatic pressure. P d is equal to the P minus the hydrostatic pressure. Okay. Now, how do we solve these equations? Okay. So, we make a series of approximations here. These are called the Boussinesq approximations. First one, density variation is linear, okay, function of temperature variation. I told you that higher temperature means a lower density, okay, and lower temperature means a higher density. Okay. So, therefore, I can write rho minus rho infinity is equal to rho infinity beta into T minus T infinity. Okay. Okay, so, lower temperature means higher density and higher temperature means a lower density. Okay. Where beta is called the thermal expansion coefficient. Okay, beta is called the thermal expansion coefficient. It can be calculated for different gases. You can calculate values of beta. Okay. Okay. Next thing. Okay. Density replace by rho infinity in all terms except the body force. Okay. You are replacing the density by rho infinity in all terms except the body force. Okay. Okay. This is valid for rho minus rho infinity by rho infinity is much smaller than 1, that is the density variation with respect to the density far from the object, that is much smaller than 1. Okay. So, when rho minus rho infinity by rho infinity is much smaller than 1, you can replace the density by its average by its value far from the object. Okay. And this basically implies that beta, okay, into T minus T infinity is much smaller than 1. Okay. The thermal diffusion, the thermal expansion coefficient times the variation in temperature between the object and the bulk is much smaller than 1. Okay. That is the second condition. Okay. This automatically implies that the mass conservation equation okay, which is divergence of rho v can be replaced by is equal to 0, okay, can be replaced by divergence of rho infinity v is equal to 0. Okay. And that in turn implies that since rho infinity is a constant, you get the divergence of velocity is equal to 0 in the mass conservation equation. Okay. You get the divergence of velocity equal to 0 in the mass conservation equation. Okay. And the third approximation is that the viscosity is considered a constant. The viscosity is considered a constant, that is you do not include the temperature variation with viscosity when you in the Navier-Stokes equations. Okay. So, therefore, the equation basically becomes rho infinity into V dot grad V is equal to minus the divergence of the dynamical pressure, pressure minus the hydrostatic head for constant density rho infinity. Okay, plus mu infinity del square V, okay, plus rho infinity beta into T minus T infinity into G, okay, rho infinity into beta into T minus T infinity into G. Okay. The only place we are taking into account the effect of the density variation is in this body force term. Okay, that is the only place we are taking into account the density variation. That is because if we do not take the density variation into account here, then there is no driving force. Okay, so there is no reason for flow. Okay, there is no reason for flow if we do not include the density variation here. That is the reason that the density variation is taken into account, okay, in this case. Okay. And finally, we also assume that thermal conductivity is a constant. Is a constant. Okay. With that, the temperature equation becomes V dot grad T is equal to the thermal diffusivity far from the object times del square T. Okay. So, that those are the equations. Okay. So, the equations have reduced to del dot V is equal to 0, rho infinity V dot grad V is equal to minus gradient of the dynamical pressure plus mu infinity del square V plus the body force term rho infinity G into T minus T infinity into G, okay, the body force term. And the temperature equation becomes V dot grad T is equal to alpha infinity, the thermal diffusivity far from the object into del square T, okay, where alpha infinity is equal to K infinity by rho infinity Cp infinity, okay, far from the object. Okay. So, those are the approximations that are made. Okay. Under what conditions can you neglect the density variations throughout the fluid? Okay. Under what conditions can you neglect the density variations throughout the fluid, okay, except for the body force term? Okay. Under what conditions can you neglect all the terms in the density equation except for the body force term? Okay. So, let us consider this for a gas. For a gas, you normally expect the pressure variation to be larger. In liquids, in a gas you would expect the density variations to be larger. In liquids, you expect the density variations to be smaller. So, let us explore for a gas under what conditions are the density variations can be neglected. Okay. So, ideal gas. Okay. At constant pressure, the density rho is equal to P m by R T. Okay. Let us assume that we have a constant pressure system, that is a reasonable approximation. The pressure is 1 atmospheric pressure. Okay. The variation in density with temperature. Okay. 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 The change in density due to a temperature variation delta rho will be equal to one by rho d rho by dt, okay, at rho is equal to rho infinity into delta t, okay, which also I can write it as, I am sorry, I should write this as delta rho by rho infinity. Okay. Okay. So, the change in density is d rho by dt times delta t at constant pressure. Okay. Therefore, delta rho by rho infinity, okay, is equal to 1 by rho d rho by dt in at rho is equal to rho infinity into delta t, okay, which is d log rho by dt, okay, at rho is equal to rho infinity into delta t. Okay. And since rho is inversely proportional to the temperature, d log rho by dt is 1 over T d d rho by dt. Okay. So, therefore, I will get delta rho by rho infinity is equal to minus delta t by T infinity. Okay. rho goes as Pm by RT, therefore, d rho by dt goes as minus Pm by RT square, that is minus rho by T. Okay. So, d log rho by dt goes as just 1 over T. Okay. For an ideal gas, delta T is the temperature difference between the object and the ambient fluid. T infinity is the temperature in the ambient fluid in Kelvin. Note that for an ideal gas law, the temperature is expressed in Kelvin. Okay, for the ideal gas law, the temperature is expressed in Kelvin. So long as delta T, the change in the difference in temperature between the object and the ambient in Kelvin is much smaller than the absolute temperature, the change in density is much smaller than the absolute density. Okay. So, for an ideal gas, this works so long as the difference in temperature between the object and the ambient is much smaller than the temperature in Kelvin, the absolute temperature in Kelvin. Okay. So, this will work for many practical applications where you, for example, the body temperature is of the order of 38 degrees centigrade, ambient temperature is of the order of 25 degrees centigrade, difference is 13 degrees centigrade, whereas the absolute temperature is 298 Kelvin. Okay. So, 13 divided by 298, okay. So long as that is small, this will be valid. Similarly, for the density, okay, we know that for a gas, the density for an ideal gas, the viscosity, okay, for an ideal gas, the viscosity mu is proportional to the temperature to the half power. Okay, it is square root of temperature, because that is the fluctuating velocity in a fluid. Okay. Therefore, delta mu by mu will be equal to mu infinity will be equal to 1 by 2 delta T by T infinity. Okay. You can do that just by taking the logs. Change in viscosity divided by the viscosity of the ambient fluid scales as 1 by 2 times delta T by T. So, once again for an ideal gas, this is valid so long as the difference in temperature between the object and the surroundings is much smaller than the absolute temperature itself. Okay. So, it is under these conditions that the Boussinesq approximation is valid. There are also changes in the thermal conductivity. Okay. That also goes as K is proportional to the absolute temperature to the half power for an ideal gas. So, you get a similar expression. The specific heat and so on vary very little. Okay. The specific heat for an ideal gas is a constant. For real gases, it varies very little. Similarly, for real liquids also it varies very little. Okay. In the case of liquid, once again you can assume the density to be approximately a constant. The viscosity does change. Okay. So, one has to be careful, check whether the viscosity variation over the temperature range is much smaller than the absolute viscosity itself. Only then will the Boussinesq approximation be valid. Okay. So, those are the conditions under which the Boussinesq approximation is valid. Density approximation is a good approximation both for liquids and gases. Viscosity has to be checked. In case of liquids, it may vary a lot. Specific heat and thermal conductivity are approximately a constant. So, the Boussinesq approximation works for those two. Okay. Good. So, these are the equations we have to solve. Okay. First of all, this length scale, okay, if you take the length scale is equal to, okay, the characteristic length of the object. Okay. Scale temperature, okay, which we usually do when there is a temperature difference between T naught and T infinity, T minus T infinity by T naught minus T infinity. Okay. The velocity scale, okay, we do not yet have a scale for the velocity because there is no characteristic velocity in the system. Okay. So, we will just assume a characteristic velocity and later find out what that is, okay, where Vc is the characteristic velocity. Okay. The gravitational acceleration vector is scaled by, okay, by its magnitude. The gravitational acceleration vector is scaled by its magnitude. Okay. And if you scale the pressure, the dynamical pressure, you would expect it to go as rho infinity V c square. Okay, you would expect the dynamical pressure to go as rho infinity V c square. That comes from the Boussinesq approximation, okay, in the inertial limit. Okay. We can substitute that into the equations. Okay. First of all, the velocity equation. Okay. First of all, the velocity equation. Okay. Del dot V equal to 0, you are scaling it by the length scale and the velocity scale. Okay. So, you just get divergence of the scaled velocity is equal to 0. Okay. That is for the velocity. Momentum equation. Okay. First term rho infinity times the velocity square by the length scale. Okay. V dot divergence grad of gradient of the velocity vector V dot grad V. Okay. Is equal to the pressure. Okay. So, here I have substituted that del star is equal to L c into the grad, okay, because the grad has dimensions of 1 over length. So, if you multiply that by the characteristic length, you get the dimensionless gradient. Okay. Pressure scaled by rho V infinity V c square. So, I will get rho infinity V c square by L c. Okay. Okay, I should have a minus sign in front of the pressure. So, let me put that. Okay. Divergence of the dynamical pressure, okay, plus, okay, viscous term, okay, the viscous term velocity by length square. Okay. So, I will get u infinity V c by L c square, okay, divergence square of the velocity, okay, plus rho beta into t minus t infinity. Okay. So, beta into the magnitude of the gravitational acceleration. T minus t infinity is t naught minus t infinity into t star, okay, into the scaled gravitational acceleration scaled by its magnitude. Note that gravitational acceleration is a vector. So, it is scaled by its magnitude. Okay. Okay, so, these are the terms in the momentum conservation equation. Okay. We still do not have a scaling for the velocity. Okay. We still do not have a scaling for the characteristic velocity in this case. We can get a characteristic scale either by balancing the inertial terms with the forcing, okay, or by balancing the viscous term with the forcing. Depends on whether inertia is large or viscosity is large. Okay. In both of these cases, you will get different results. Okay. So, in this case, we will balance the inertial terms. Okay. With the gravitational or body force. Okay. So, I get rho infinity V c square by L c, okay, balanced against rho infinity beta g into t naught minus t infinity. Okay. And comparing these two, I will get the characteristic velocity is equal to root of L c beta into t naught minus t infinity times g. Okay. This is the characteristic velocity that we get by balancing the body force against the inertial terms. Okay. This is the characteristic velocity that we get by balancing the body force and the inertial terms. Okay. Next, we have to find out scale the equations using this characteristic velocity in order to express the equations in terms of dimensionless groups. That I will continue in the next lecture. I will go through the scaling of the equations and show you what scaled variables arise, and once that is done, we will then go on to looking at how we can get solutions for the equations We will not solve the equations completely, but rather we will get magnitudes of the heat transfer rate in each of these cases. I will continue this in the next lecture. Natural convection, the Boussinesq approximation. I will continue this in the next lecture. I will see you then.